Welcome to week infinity of the lockdown. As you can see, I have regrown most of the beard, and hopefully your hair is looking better than mine. So let's jump into a problem. This is problem 20-2 in the one section of chapter 20, dealing with general motion in 3 dimensions. So we have this object that is rolling along the surface, and we're told that it is rolling without slipping. And the idea here is that imagine that you have something like a thumbtack, or I have done this with some of my son's Legos, where I have an object that is both rotating about a given axis, and also, there we go, a little bit better, and then seemingly rotating about a given point. And we are told that it is rolling without slipping about this point of contact here. And we want to find the acceleration and velocity of this point A. So as always, we first have some geometry. I'm going to go ahead and also add some labels to these. So the point that's in contact with the ground, that's instantaneously at rest because it's rolling without slipping, is point B. I'm going to call point C the center of that disk up there. We're given this distance from C to A and this distance from the origin, which I'll call O, from O to B, of 300. So if we were to redraw that triangle, we would have 300 millimeters there from O to B. If I look at point C, that would be 150 millimeters. And then as you sort of notice these ratios, since this is twice that, if I connect O to C, this is going to make a 30, 60, 90 right triangle. So we have 30 degrees here. That also means when I go up and connect to A, even though I draw it a little wonky, this is also going to be a right triangle. So in fact, this entire OAB is an equilateral triangle. That's going to make things a little bit simpler. So in terms of distances, we're going to need to know the distance from O to C. So this is 300, that's 150. The distance from O to C is going to be 150 times the square root of 3, or approximately 260, and all of these distances here are in millimeters. Now, there's a couple different ways in which we can approach this problem. If you look through some of the examples in the text, it immediately starts in with looking at the angular velocities. I want to start with something that hopefully is a little bit more familiar with us, and that is first approaching this as an instantaneous center analysis. Because we are told in the problem that it is rolling without slipping, and that means automatically that point B is going to be an instantaneous center for this rotation, and this will come back and help us multiple times. So that means as we look at what's happening in here, instantaneously, this wheel is rotating. In fact, we have what I'll call an omega C rotating about this axis OC, in addition to the separate rotation, which the book calls omega Z, which is this rotation about the Z axis. So again, we're in 3 dimensions. Rotations are a little bit trickier to deal with, and we'll come back and talk more about this later. But instantaneously, for example, I can view the velocity of point A, which is one of the first things we're trying to find. Notice since it's lying along the YZ axis, its velocity at this moment is going to be pointing in the negative x direction, which means it's going to have a unit vector pointing in the negative I direction. In terms of magnitude, again, since it is rotating with some frequency omega c, and we have this distance between A and C, we can say that VA is going to be equal to 300 millimeters multiplied by omega c, where omega c is an unknown. But I can do the same thing looking at point C. Again, the center of this wheel is also moving. It's going to be moving in this direction, and so I could write down that its velocity would then just be equal to 150 millimeters times omega c. However, we're told this rod OC is rotating about the Z axis. So in fact, this whole rod is undergoing a rotation. And so if I look at the distance between this axis and C, I'm going to call that Y sub C. Then it also has to be the case that the velocity of point C has to be that distance YC multiplied by that angular velocity they told us, omega Z. So coming back to our triangle here, if we drop this down here, This distance here is going to be that YC. And if we work that out, we get that YC is equal to exactly 225 millimeters. So if this is 225 and this is equal to 0.5, then we can then divide by 150. This gives us that omega C is equal to 0.75 radians per second. And then we can plug this back into VA, and we get that VA is equal to 225 millimeters per second, or if we want to write it as a vector, V sub A is equal to 0.225 meters per second, acting in the negative I hat direction. Now, this is when I said we have to be careful how we think about these rotations, because the next thing we would want to find is our acceleration of point A. So our VA vector was an unknown, and we just found that. We also want to find the acceleration of point A as an unknown, and that's going to be a little trickier. Now, we've already talked about two different angular velocities. We said we had this omega z, which would point in the k hat direction, and then we would have this omega c, and notice how we're rotating it here. Since this is rotating this way by the right-hand rule, this would actually represent an angular velocity vector pointing down at that angle. So if we wanted to write these as vectors, we would have omega z is equal to 0.5 k hat, and then omega c is equal to its magnitude, which is 0.75, multiplied by a unit vector pointing in that direction. It's pointing in the negative z and negative y. This would be negative cosine 30 degrees j hat minus sine 30 degrees k hat. Again, because this here is forming a 30-degree angle. So multiplying that through, that would give us negative 0.650 j hat minus 0.375 k hat. I've got two different angular velocity vectors. Which one of these is the true angular velocity of this object? Because only one single vector should describe the angular velocity. And it turns out that neither of these is the true angular velocity, nor is it the sum of these two vectors. I can't just add these together. The issue is that even if this rotates at a constant magnitude, and omega c is of a constant magnitude, our angular velocity vector omega is going to change direction because it is rotating in 3 dimensions. So even though they're both constant, its direction is changing. We saw this similar when we looked at uniform circular motion, where our tangential velocity was fixed in magnitude, but also changed direction. In fact, when we looked at circular motion, uniform circular motion, we had a relationship between our tangential velocity and our radial vector, and these will look familiar because we're still using them. Centripetal is equal to omega cross v sub t. And notice, finding the derivative of a given term is equivalent to just taking omega cross that term. That is something that is talked about more in section 20.2, but that gets a little bit complicated there. So when we want to similarly go write down what our velocities are, if we wanted to say that the velocity of point A is equal to some omega cross RA, where RA is going to be this vector pointing from O to A, and then we would want to write down a similar thing for our acceleration. The acceleration of point A is going to be some alpha cross R plus omega cross R. We first off don't know what our omega is, and second, we are going to have an angular acceleration because, as we said before, our omega is changing direction. So what we need to do is we want to find out first what this omega is, then use that to find alpha, and then we can plug that back in to find our A sub A. Well, the first thing we know is that if we were to write down our R sub A, again, just using the information up here, that is going to have a value of 150 millimeters along J hat plus 260 millimeters along K hat. And let's assume for the moment that we don't know any of the components of our omega. So I'm going to call them omega 1, 2, and 3, because we're already using a subscript z up there. Again, it's a three-dimensional vector. It could have three components. However, I do know that this relationship should hold. Our v sub a, which we know as negative 225 millimeters per second I hat, should be equal to omega cross r, or this big vector, omega 1 I hat plus omega 2 j hat plus omega 3 k hat, crossed with 150 j hat plus 260 k hat. Again, work out those cross products, and notice that since we only have an I component here, I can only have I components on the left-hand side, so that immediately tells us that my omega 1 is going to be equal to 0. However, the equation that we do have left over says negative 225 is equal to 260 omega 2 minus 150 omega 3, which is two unknowns, but with only one equation. Now, back to our instantaneous center analysis. We said that B is an instantaneous center. Not only that, but the axis OB is also, everything here is at rest because point O is not moving, point B is not moving. So in fact, it must be rotating about that axis, which means that our angular velocity vector must also be pointing along that direction. It can only have a positive j hat direction. So coming back up here, this means that our omega 3 also has to be equal to 0. So therefore, that term goes away. The only thing we have left is our omega 2, and that's going to be equal to negative 0.66, not 666, come on there, radians per second, and that's acting in the j hat direction. All right, this is going to have to be part 1 of the video because I'm already filling up most of the page, and my iPad is about to die, so hold on for part 2.